We're now going to talk about part 2 of our discussion on the structure and functionality of the Java fork join pool framework. And so now we're going to move away from talking about ForkJoinTask to other elements, in particular the various implementations and subclasses of ForkJoinTask. So programs typically don't use ForkJoinTask directly. Instead, they extend a subclass of ForkJoinTask and override its compute hook method. And you can see there's a bunch of different variants of subclasses of ForkJoinTask. We have recursive action, recursive task, and counted completer. And we'll talk a bit about these things. So recursive action is the subclass of ForkJoinTask that's used when computations do not return results. They just do computations, and then they're done. And so as you can see, it returns void, which means it doesn't return anything. It's just a void. Recursive task, which is kind of the workhorse for most of the things we're going to look at, is used for computations that do return results. And as we'll see, it returns results. And then counted completer is used for computations in which completed actions trigger other actions. And this is not used commonly by applications, but it's used a lot by the Java frameworks, and it's used heavily by the Java Streams framework. Interestingly enough, ForkJoinTask is not an interface, and it's a class, and therefore recursive action, recursive task, counted completer, and so on are not functional interfaces. And therefore, you have to actually extend or subclass them rather than using lambda expressions to implement the compute hook method. And this is a bit of a shame. This is probably a sign of this is probably a result of the fact that ForkJoinPool was added to Java in Java 7 in the 2010 timeframe, prior to the functional programming features being added in 2014. So I think if they had a chance to redo it from scratch, they might have made ForkJoinTask an interface with a compute method, and that would have been the one abstract method, and all the other things could have been functional interfaces, and it would have greatly simplified the way in which you implemented the code. But they didn't do that. They didn't have the luxury of being able to completely destroy backward compatibility, so we're stuck with this approach. What it really means in practice is it's just a little bit more syntactically dense than might otherwise be the case, and we'll see that when we look at the examples here shortly. Now, one of the cool things about this is if you want to stick with the functional programming paradigm, you just have to use the Parallel Streams framework, which gives you a functional API that encapsulates all the ForkJoinPool stuff. So all is not lost. Functional programming can still be used with the ForkJoinPool. It's just that it's hidden from you by using the Parallel Streams framework. Now, there's a bunch of different methods on ForkJoinPool. It implements the various executor service methods, so you can go ahead and execute callables and runnables. But by far the most common and useful things for it to do are execute various ForkJoinTasks or invoke, submit, and so on, various ForkJoinTasks. And there's a couple of different ways to look at this. This perspective is sort of from the most external view. So if you have an instance of a ForkJoinPool and you want to set the wheels in motion, then you will come and make invocations to these API calls defined on ForkJoinPool: execute, invoke, and submit. And we'll come back and talk more about these methods later. The main point to come away with at this stage is that these methods are used to get the initial ForkJoinTask into the ForkJoin framework. And once it's in the ForkJoin framework, then all the magic of the worker threads and the work stealing and all that stuff takes over. And we'll talk more about that. So what happens here is that when a client, in other words, a program that's using a ForkJoinPool, wants to start things in motion, it will insert new tasks it'll insert new tasks by calling one of these methods like execute, invoke, or submit. And it puts these new tasks into a shared queue that's used to feed the various work stealing queues that are managed by the worker threads. So this is kind of what it looks like. So you have a client over here, and a client submits something, and it goes in this shared queue. And then the threads that are running in the worker pool will come up and take the item off of the shared queue, if there is one, if they come there and they find one's there. They'll take an item off the queue and then go ahead and will push it onto that worker thread's work stealing queue, which is really this thing called the deck. And so at that point, then things can start running. And remember, as things get pushed onto one deck, then another thread in the pool can come along and steal that work from the end of the deck and then start to process it. So that's how you can quickly disseminate work that's picked up from this shared queue to all the different worker threads that are running in the fork join pool. We'll come back and talk more about this later. It's very important to understand this. The whole purpose of work stealing, as I've mentioned several times, is to try to maximize core utilization. We want to keep things as busy as we possibly can. And so if, much like the Jiffy Lube model we talked about, if someone's sitting around in a bay where there's no car, they're going to walk over and start being useful by pitching in, helping get another car out faster. So the goal is to keep everything humming along and making the whole enterprise run as quickly as you can. There are intentionally very few knobs that can control a fork join pool. Basically, all you can really do is, make these API calls to execute, submit, or invoke these methods. You can shut down the pool, check to see if it's been shut down. There just isn't a whole lot of things you can do. It's kind of like a one-button mouse. And that's in contrast to the ThreadPool Executor framework, which is another implementation of the executor service interface. And it has gazillions of policies and options and flags and so on and things you can do to make it do stuff. So it's kind of like, imagine this sort of a mouse, right, which has got, like, I don't know, a dozen buttons. So it's very complicated to use, very flexible, but maybe you're better off with one button. But for whether or not, leaving aside any value judgment, Fork Join Pool has very few knobs. ThreadPool Executor has lots of knobs. We'll talk more about ThreadPool Executor next semester. Here are just some of the things you can control in the ThreadPool Executor: the size of the pool, the core size, the max size. You can set the work queue. You can determine how long threads in the max pool size pool will live if they're not active. You can create a factory that will make threads for you. If you can't process work when it's submitted, you can come up with a way to handle its rejection, and so on and so forth. The one thing you can do, or two things you can do actually, is you can configure the size of the common fork join pool using the system.set property, and you can also affect the number of threads by using the manage blocker interface on the common fork join pool. So we'll come back in a few lessons to talk more about how that all works. It's very important to understand. Okay, so that's the overview of the structure and functionality. You still may only have an inkling of how things work, and don't worry, by the time we're done with all these lessons, you will have a very good understanding of how the fork join pool works, but it's a complicated framework and it takes a while to explain.